scary thing to be in an earthquake. Everything shakes. Buildings fall down. Cracks appear in the ground. People may be killed. And anyone who lives near a volcano should be prepared to leave. You don't want to be around when this happens. Or this. This damage was caused by a tidal wave created by an undersea earthquake. Dozens were swept to their deaths. So why do these things happen? What's going on underground? It turns out that when the Earth starts pushing and shoving, volcanoes and earthquakes are just a small part of a bigger picture. Deep within the Earth, enormous heat pushes outwards. Its most obvious effects are in places like this, where molten lava flows from the ground, or where hot water and steam boil up. But this is nothing compared to what it can do. The Earth beneath our feet is literally moving all the time. Australia is moving, as is every other piece of land on Earth. The map of the world is very slowly but relentlessly being remade by the heat engine of the Earth. When you look at the map, the shapes of many coastlines suggest that in the long-distant past, they may have been joined together. Years ago, people reworked the map like this and proposed that there was once a supercontinent which they called Pangaea. At first, Pangaea was just a fascinating guess, but then more evidence began to trickle in. For example, these are the scars of ice scraping across rocks in South Australia. Similar scars of the same time period are found in South Africa, South America and India. A strong hint that these areas were once near the South Pole. Other evidence, like the magnetism left behind and matching rock types, made the guess look like a fact. Present continents were once joined in a supercontinent at the South Pole. Pangaea existed. But what had split it up and pushed the continents into their present-day positions?
The answer is in the heat of the Earth. Watch what happens when I boil some water. I've put some beans in here so you can see the movement. Now, the water above the flame expands. It rises to the surface, while the cool water spreads down and around the outside of the pot. This circular movement, driven by a hotspot, is called convection. Now, if I put a cork in here, it floats, but it's pushed to the side by the hotspot. I want you to imagine this cork is a continent. Now, you're starting to get some idea about what's happening. This is a simple model of what we think takes place deep inside the Earth.
In the 1960s, 2/3 of the planet was still unmapped, but the invention of the echo sounder changed that. Sounders revealed underwater mountains. Later, new deep-diving subs actually saw what was going on. Volcanoes in the deep sea, smoke and hot rock coming out. When scientists finally mapped all the volcanic ridges under the seas, they were amazed to discover long lines of them. These fiery splits run right around the planet under the sea. You didn't have to be a genius to see that this was where the movement came from. Just as in a boiling pot, heat inside Earth drives convection currents in the mantle. Slowly, but with enormous force, extra hot rock forces its way upwards, pushing the slightly cooler rocks sideways. This sideways motion drags underneath the deep ocean crust, pulling it apart right where the heat is greatest. Released from huge pressure, the rising rock turns to liquid. It becomes magma and pushes into the ever-growing gap. Seawater then cools it into solid rock. The result is that a new ocean bottom is being created, and it creeps out either side of the volcanic ridge by a few centimetres every year. And that's about how fast the continents move, about the same rate as your fingernails grow. They move because each continent is embedded in a vast plate of moving sea floor and is carried along with it. The name given to these is tectonic plates, meaning plates from which the Earth is built. Where tectonic plates meet, they push against each other, and not surprisingly, something has to give. One of them is driven under. Where sea floor meets sea floor, it's a toss-up which one goes down. But where a continent rides on the edge of a plate, there is no contest. The sea floor is always the loser. It returns to the mantle.
This piece of rock comes from the seafloor. It's basalt. And this other piece of rock is typical of most of the rock of the continents. It's granite. See how they're different? The granite is much lighter in colour, and what you can't see, but I can feel, is that it also weighs a lot less than the basalt. It's less dense. So what this means is when large quantities of these rocks are forced together, the basalt tends to slide underneath the granite. This is why the rocks of the continent tends to stay separate to the rocks of the seafloor. They stay on top, while the basalt plunges its way back down into the mantle.
About 200 million years is the time it takes to recycle the biggest piece of ocean crust. That's the time to get from the spreading ridge to the zone of subduction. If that sounds like a long time, some rocks on land are 20 times older than that, almost as old as Earth itself. These rocks in Western Australia are more than 2,700 million years old, showing that this slab of the continent has stayed on top of the mantle for over half the age of the Earth. But even though most of the continental slabs have apparently never sunk, they have been split and battered as they moved around the world. Where continents sit on the plate edges, their rocks are often buckled and pushed up into mountain chains. New Zealand sits right where the Australian plate forces against the Pacific plate. The New Zealand Alps are still being built where the two plates grind and push together. In fact, New Zealand was created by this action. These mountains are still being uplifted at up to 8 millimetres a year. Another result of plates pushing and shoving is volcanoes and hot springs. Deep beneath this ground, about 100 kilometres down, the sinking ocean crust is finally melting. Plumes of magma are rising up, heating the ground and the water it contains. If the plumes are big enough and hot enough, they can also burst through as volcanoes. New Zealand's position makes it tectonically active. But Australia, for the most part, is not. The reason is that Australia is not at the edge of its plate. It's near the middle. Whatever mountains and volcanoes we once had are now very eroded, but the rocks still show the evidence of long distant times when things were different. For example, the Darling Scarp on the west coast is evidence of pushing and shoving on this side of Australia, which started well over 1 billion years ago. In the east, the Australian Alps were lifted up about 100 million years ago. These are but two of many examples of past tectonism, which helped to build Australia from west to east over some 4 billion years. So there is plenty of evidence of geological pushing and shoving all over the place. Here the rocks have been broken. You can see the split through them, which is called a fault. Faults come about when the Earth's crust is pulled apart or pushed together.
Faults can basically happen in three ways. If the two rocks are being pulled apart and one side slips beneath the other, this is a normal fault. Or, if the rocks are being pushed together and one side rises up above the other, that's a reverse fault. The third kind of fault occurs when the two rocks slide past each other like this. This is called a strike-slip fault. Faults usually occur really fast as the pressure grows and grows, and then bang! The rocks break. A big fault can cause an earthquake.
It sometimes surprises people that we get earthquakes in Australia. But although most earthquakes are definitely at plate boundaries, they can happen anywhere that strain builds up. Most earthquakes in Australia are small ones, but the irony is that they are also mostly shallow and close to the surface, and that means they're closer to us. This was Newcastle in 1989. 12 people killed, $4 billion damage. However, rocks under strain don't always fault. Amazingly, they can also bend and fold, like putty. Yet these rocks are as hard as nails. How could they twist into such shapes?
The answer is simple. In fact, putty or Play-Doh show it well. If the force on the Play-Doh is fast, it breaks. But if we rejoin them and use slower force, they don't break. They deform and fold. So if the pressure on rocks is slow, they tend to fold, not fault. Also, temperature. Freeze your putty in dry ice and it goes very hard and snaps. Rocks near the surface are cold and hard. They tend to snap, but deep underground, as it gets hotter, they're soft. And kilometres underground, the pressure is enormous. What's happening is something like this. These sand layers fold and fault as pressure is put on them from the end of the box. Like this sand, the rocks underground are being pushed and shortened, so they too fold and fault.
The pushing and shoving of the Earth's crust is a perfect example of something that we don't notice happening most of the time because it is so slow. Then we get a nasty surprise when a volcano erupts or an earthquake happens. What we should be doing, however, is realising that the face of the Earth has been made and remade many times before now, and that the forces of heat deep within are still at work. Australia, for example, will continue to drift towards the equator, and the world map will eventually look nothing like it does today. Nor will the face of the land look the same. For while rocks are pushed up, where they are exposed, they're also attacked by sun, wind, and water, slowly cracked apart, dissolved, crumbled, and turned into dust and sand. The rocks of the high places become the rocks of the low places. So while pushing and shoving heave rocks up, there are equally relentless forces tearing them down.
Online teaching resources to support this program are available at abc.net.au/SchoolsTV.